Okay, so question number 3. The electron configuration of a gallium-3 ion, gallium-3 plus, is which of the following? Okay, so to answer this question, we need to write down the electron configuration of gallium. So finding the electron configuration of an element in its ground state will help us determine its electron configuration when it is an ion. So in the case of gallium-3 plus, this means it lost 3 electrons. Okay, so I'll write out the steps of finding electron configuration. So the first step is to divide your periodic table into the different orbital sections. Such as S, E, D, and F. Okay, so I'll show what this will look like. Already divided. Okay, so here's an example. And the first 2 columns, including helium, is known as the S block. This green section is the P block. And the middle transition metals are the D block. And finally, the last 2 rows, the lactanides and actinides, is the F block. Okay, so step 2, starting from hydrogen, we move left to right across the periodic table writing the row number followed by the block letter. And step 3 is that we can show how many electrons are in each orbital or suborbital using superscripts. Okay, and I'm also just going to add for step 2 that when we write the row number, when we get to the D block, we write the row number -1. And when we get to the F block, we write the row number -2. Okay. So let's try to do our example, which was the electron configuration of gallium. So gallium in its ground state can be found right here, atomic number 31. So starting from hydrogen, we can write the row number, which is 1, the block letter, which is S, and show how many electrons are in each orbital using superscripts. So in the S orbital, it can hold a maximum of 2 electrons. So we just put 2 in the superscript. And then we move on to the next row. So row 2, S, and then 2. Then we move over to the P block. So we write 2P 6. And this is because a p orbital can hold a maximum of 6 electrons. Okay, so on to the next row. We have 3s2, and then again 3p6. Down to the next row, we have 4s2. And now once we get to the D block, you'll see that we went down a row. So we did row number -1. So now it's 3d10, since the d orbital can hold 10 electrons. And then finally 4p1. Okay, so now we have our electron configuration in the ground state. Okay, so now when gallium loses 3 electrons, we need to draw the new electron configuration. So if we were to lose 3 electrons, we would actually lose the electrons in the 4 orbitals, so 4s and the 4p orbitals. And this is because our 4s and 4p orbitals for gallium are higher in energy. And it'll actually be easier to lose these electrons than it would to lose the electrons of a 3d10 orbital. So I'm just going to also add that the 3d10 filled orbital is more stable. Okay, so now let's write our new electron configuration. It would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d10. And then if we were to write the shorthand configuration, it's fairly simple. We just need to find the noble gas that comes before gallium, which in this case is argon, and we write argon in square brackets. And then we continue on writing the remaining of the electron configuration. So in the case of gallium 3+, it would just be argon and then 3d10. Okay, so let's see what the junior tutor said. I guess our option here would be option A. And they also showed that the 4s orbital and 4p orbital have 0 electrons, and it ends in just 3d10. So option A would be correct. And the junior tutor said that in writing the electron configuration of an element, we follow the Aufbau principle, which states that the order of energy will dictate the order in which electrons are arranged in their orbitals. Therefore, the lowest energy will be occupied by electrons first. Okay, so they also drew out a helpful picture to help show the order of 1s, 2s, and then 2p. And they said that gallium in its ground state has 31 electrons with the electron configuration of the following. Yep. And when it loses 3 electrons, it forms gallium 3+. Therefore, 3 electrons will be lost from its last subshells, 4p and 4s, resulting in the electron configuration. Yep, which is the same, so this answer is A. Okay, so this solution is correct.